All right, so in this video, we're going to talk about partial derivatives. Before we get really going with finding these partial derivatives, I think it's important to take a step back and realize that one of the more fundamental questions in calculus is finding the equation of the tangent line to the curve. Now we've upped it a little bit in terms of a higher dimension, and we can be talking about surfaces. And much like we saw in the last section with limits, there are infinitely many ways we can approach these certain points. And so we've narrowed it down at this stage to two pathways. We're going to be talking about partial derivatives of f with respect to x and partial derivatives of f with respect to y. The partial derivative of f with respect to x is approaching along a path that is parallel to the x-axis. With respect to y is going to be approaching on a path parallel to the y-axis. The book has a figure in your text. This is on page 811. It's figure 14.18, where they actually have a nice diagram in there explaining and showing how with respect to x is going to be parallel with the x-axis, and with respect to y is going to be parallel with the y-axis. If we want any other direction, then we'll change our focus into studying directional derivatives in a later section. So back to where we are now. So partial derivative of f with respect to x. So first thing is some notation. That is going to be denoted either by an f with a subscript x. That's going to be your partial derivative of f with respect to x. Additionally, you might see the notation that looks like this, where we've got a curly d f and then a curly d x. And so it replaces the the dy dx that we've used for Calc 1 single variable derivatives. So we've got partial f, partial x, and it kind of looks like a curly d. So partial f, partial x. And then using that limit definition of a derivative, we would have limit as h approaches 0 of f of x plus h comma y minus f of xy all over h. Now that's not really any different than anything you would have thought, because if we're approaching along a direction parallel to the x-axis, then the x would be changing, the y would not. In fact, what that means is that in fact y is a constant. So hang on to that little bit of knowledge for down the road. So partial f, partial x, y is going to be a constant. We've got our x changing by h, and we've got our function now of two variables, x and y. All right, so that is the partial of f with respect to x. When it comes to the partial of f with respect to y, it's pretty similar. We'll have an f sub y notation. We'll have a partial f, partial y, and we'll also have a limit now as k goes to 0 of f x comma y plus k minus the function itself all over k. So much like the last one, as I pointed out, now your y is going to be what's changing, since we're approaching along a pathway parallel to the y-axis, and therefore x would be constant. So x is constant in this case. Another important thing to hang on to, much like from above. So those are your two limit definitions. We'll go ahead and take a look at an example, and then we'll jump into a few more direct ways. All right, so here's our function here of x and y. And in this particular problem, we're going to find partial f, partial y using that limit definition. Okay, so partial f, partial y using the limit definition. That's going to be the limit as k goes to 0. Then we'll have the function, and the x's are going to be constant, so nothing changes there. But every place you see a y, you're going to need to replace that with y plus k minus the function itself all over k. So this part here is going to be our f of x, y plus k. This is going to be our f of x, y, and then of course we have our k down below. All right, so we'll go ahead and simplify this now. So partial f, partial y is going to be the limit as k goes to 0, and this will be x squared minus y squared minus 2ky plus k squared. Excuse me, that's a minus k squared there. minus k squared. And then we have minus x squared plus y squared if we distribute that negative in there. Now, just like in Calc 1, everything without a k should go away. So x squareds are gone, y squareds are gone, and therefore everything that we have left has a k in it, so I can factor that k out. If I factor the k out, I'm going to be left with a negative 2y minus k over k. These will divide off, and then if we go ahead and evaluate our limit as k approaches 0, this guy right here would also zero out due to the limit. So the limit takes that to 0, and we have then a final answer of negative 2y. So that's using the limit definition. And if you remember, a moment ago I described the partial derivative of f with respect to y, where x is considered a constant. So if we come back up here and we actually look at the original, if we take this derivative knowing how we have done so in Calc 1, where x is a constant, notice how this constant would go to 0, and then since we're with respect to y, we would take this derivative normally. 0, multiply the 2 down, keep the inside the same, subtract 1. It does in fact give us the same answer, and that's how we'll be taking the derivatives now moving forward. All right, so for the next example, one where we're not going to use the limit definition, I've chosen a function with 3 different variables, which means that we can actually find 3 different partial derivatives. We can find f sub r, we can find f sub s, and we can also find f sub t. And I found that using an example with multiple variables really emphasizes the point on how to treat things as either a variable or a constant. So, for example here, if we start off with f sub r, that means that r is the only thing in here that we care to take the derivative of as a variable. That also means that s and t's are all going to be considered constants at that point. So one of the things that I might do, especially early on in this process, is even possibly rewrite parts that are a little misleading to reflect what it is I'm looking for. For example, if r is going to be my variable, but my s and my t are going to be constants, I might even write it like this, where it doesn't really doesn't at all represent anything differently, but it just shows differently so that I can treat this quantity right here as a constant. Okay, so let's take a look at the first f sub r. So we're going to need to treat this as a product rule. We've got our first, and then we've got our second. So derivative of the first with respect to r. So that would be a 0. That would be a negative 2r. Then we'd have a 0, and we'd have a 0. So this whole thing, the negative 2r, is the derivative of the first. Derivative of the first times the second. So I'll copy down the e to the negative rst. Now, plus derivative of the second back times the first. Let me go ahead and write that first down to make sure I don't forget to do that. And then the derivative of the second. And again, I'm picturing this guy to be a little easier to understand. So being an exponential, I'm going to copy the whole thing down. So we've got an e to the negative str, and then back times the derivative of the inside, which would be this. Now remember, that's a constant. So if I asked you what the definition of 7 times r is, everybody would know that the derivative of that's 7. And this is really no different. This is a constant, so the derivative of this part is going to be a negative st. So now moving on to f sub s. Now, s will be considered our variable, and every other thing here will be considered a constant. So it might be helpful now to rewrite possibly this guy here as e raised to the negative rt with the s off to the side. And again, that's purely optional, but it's something that early on will be quite helpful. So derivative of the first. So derivative of the first with respect to s, so constant 0, minus 2s. And then we have another constant 0, derivative of the first times the second, plus derivative of the second back times the first. So this is the first that I'm writing down. Now, derivative of this guy with respect to s. In a similar way to the first one, we're going to have an e to the negative rts, and then back times the derivative of the inside, which would be a negative rt. The order in which you write these doesn't matter. It's all multiplication, so I'm just kind of jumping around a little bit there, but I'm trying to make it so that it's easier to follow when we take the derivative. So that's going to be your partial of f with respect to s. And then finally, partial of f with respect to t. Let me come over here and I'll change this one last time if necessary. That's going to mean that r and s are going to be your constants. So we're going to have a negative r and s followed by a t. And we'll just follow the same pattern. Derivative of the first with respect to t would be a negative 2t, e to the negative rst. And then we've got a 1 minus r squared minus s squared minus t squared. Write it down. And then the derivative of the inside with respect to t would be a negative rs. So again, choosing an example with a lot of different variables I think is easier now to push how to treat things like constants and when using the correct form of the derivative.